Hello everyone and welcome back to another video where we are going to be doing a fun little proof from complex analysis that the sum from negative infinity to infinity over f is equal to the negative sum of the residues of this function right here, which I will call g pi times f of z times cotangent of pi z at the poles of f. And before we get started, a couple things need to be said about our function f. The first thing is that f is rational. So f is rational. And the second thing, it comes from the first, or part of it at least. Since it's rational, we can write it as some p of z divided by some q of z. So that should be a q down there. Divided by some q of z. And the degree of these polynomials should be as follows. So the degree of q should be greater than or equal to 2 plus the degree of p. And the reason for this will be explored later on in the video. But to get started in improving this, what I want to do is focus on this function g right here and find what its residues are at every single integer. So along this k right here, right? So let's go ahead and do that. So we see that, let me write it out right here. So we see that, know that g of some z is equal to pi times f of z and then times cotangent of pi z. So let's go ahead real fast and let's find the residues of this function right here at z equals, so the residues of g at z equals some integer k, right? The way we're going to do that is first by expanding g. We know that we can express this cotangent right here as just cosine of pi z and then divided by pi sine of pi z. And from that, we see that, assuming that f has no poles coinciding with this cotangent, we see that our poles here are simple poles, and they occur at every integer. So what we can, to find the residues, we can say we have z minus, well, k, where k is an integer, of course, and then times pi times f of z, and then cotangent of pi z, or if we were to expand it, we would just write cosine of pi z and then divided by sine of pi z. And what we have to do here is just take the limit as z approaches k, and that will be our residue, because after all, this is just a simple pole. Using L'Hopital's rule, we find that the denominator of all of this is just going to become pi times the cosine of pi z. But one thing we can note about the denominator is that this is never going to be 0 for integer k. If we plug an integer k into here, in fact, we actually get a pi times negative 1 to the k. So since the denominator can never be 0, we know we only have to apply L'Hopital's rule once, and any term in the numerator, after applying L'Hopital's rule, any term in the numerator that goes to 0, we know it's just not going to contribute to the limit. Period, the end. So really the only term surviving all the differentiation in the numerator is going to be the one term in which this right here is differentiated, because we plug in k. Well, we know that cosine of pi times k, well, that's not going to be 0. And f of k is not necessarily 0 either. So what we're left with in the numerator is actually just pi times f of z times the cosine of pi z. And you'll see here that a lot of these terms cancel, and we're left with just f of k right here. So really there's a limit here, limit as z approaches k. And that's what we're left with. So the residues of our function g at any integer is actually just f of that integer itself. Consider the following contour right here. If we were to take the integral of g around this entire thing, going this way specifically, what are we going to get? Well, so the contour integral of g dz, well, what are we going to get? By the residue theorem, we know that this right here must equal 2 pi I times the sum of all of our residues. But what exactly is g? Well, g right here we know to be pi times f of z, and then times cotangent of pi z. And based on this definition, we see that we have two sets of residues, really. we have the set of residues from our cotangent, which is just every integer, which we can just call k maybe. And then we also have our set of poles from f, which are unspecified. So based on this, we can rewrite this right here, this part where we use the residue theorem. We can rewrite this as follows. We can say that this is equal to 2 pi I, and then times the sum of the residues of g, but then at our integer k, so at our integer k, and then plus the sum of our residues of g, but then at the poles of f. So I'm just going to say at f to shorten that up. And some integers at f. And you'll see here something that's very interesting. This 2 pi I times, or the residues of g at k, well, we just evaluated this. We know that this right here is just f of k. So simplifying this, we have 2 pi I times f of, or really the sum of f, pardon me, the sum from k equals negative infinity to infinity of f of k, and then plus the sum of the residues of g, but then at the poles of f. And you'll see here that our formula is really starting to take shape. And the reason I should note why it goes from k equals negative infinity to infinity is because A, that's what we want to prove, but also B, we just take the limit here of this contour as n goes out to infinity. That's the way we enclose all of our poles. And the reason why we have n plus 1/2 is just to ensure that none of the poles of our cotangent actually lie on the contour itself. It's just a way to ensure that they're all inside it so we can use this residue theorem. But you'll see here that this equation right here is awfully similar to the one that we started with. The only difference being that this right here was equal to this right here. And the only way for that to be true is for the whole contour integral itself to be 0. So let's go ahead and prove that, shall we? One way we can write it, or get an upper bound for it, so that we know this is going to be less than or equal to the contour integral of the absolute value of g. But what's the absolute value of g? We can say that this is pi, or the absolute value of pi times f of z, and then times cotangent of pi z, and then dz. But let's take a look at this cotangent term right here. Let's consider the absolute value of cotangent of pi z just for one moment. We can represent z as just a complex number. We can say this is some a plus bi, right? So this right here is really equal to cotangent of pi times a plus bi. But cotangent itself is a composition of trig functions. And we know that we can write trig functions as just the exponential. We can just say cosine, for example, is e to the x, or cosine of x is e to the xi plus e to the minus xi, all divided by 2. So since we know cotangent is just cosine over sine, we can rewrite it as, or the absolute value of it, as the absolute value of I, and then times e to the pi z, plus e to the minus pi z, and then divided by e to the pi z minus e to the minus pi z. But as said earlier, we can make z this a plus bi. So really what we have is, I can drop the I because based off the absolute value, we can say this is now e to the pi a plus bi plus e to the minus pi a plus bi, and then divided by e to the pi, or e to the plus pi, a plus bi, and then minus e to the minus pi, a plus bi. And by the triangle inequality, since this is an absolute value after all, we know that this right here is going to be less than or equal to the absolute value of each part. And what I mean when I say that is that this is going to be less than or equal to, so fraction bar, e to the pi, and then times a plus bi. And then we close the absolute value, and then we have our other terms, so then plus e to the minus pi, a plus bi, absolute value. And then in the denominator, the same thing. So we have e to the pi, a plus bi, absolute value, and then minus e to the minus pi, a plus bi. And I do apologize. There should be a bunch of i's here actually. So this should be e to the zi. Focusing in on this right here, we see that whenever we distribute this I, ignoring the pi for a moment, we have ai minus b. If we can split this up into e to the pi ai and then times e to the minus b pi, right? But whenever we take the absolute value of that, we can take it term by term, since it is multiplication. And we know that e to some purely imaginary number, well, the magnitude of that is just going to be 1, because it's just going to be some point along the imaginary or the complex unit circle. So based on that, what we can do is the following. We can rewrite this. We can say this is equal to, well, the absolute value of e to the minus b pi, and then plus e to the b, or pi b, and then divided by e to the minus pi b, plus, minus e to the minus pi b. And we can drop the absolute value signs because these right here are all just going to be positive numbers. And you'll see here that we can actually simplify this one step further. We can multiply the top and bottom by e to the minus b and obtain that this is just 1 plus e to the minus 2 pi b divided by 1 minus e to the minus 2 pi b. Now, here's an interesting note about this function right here. This function right here actually looks like this right here for positive real numbers. And it's going to continue that way, and there is a horizontal asymptote at 1 actually. And the reason why this is important is because for our contour, what is the smallest b can be? Well, if we go back up here, well, the smallest b can be is just 1/2, because you'll see here, just take this point for example. If we make n we're not going to make n negative, so if we make n just a natural number including 0, the smallest this point can be, the imaginary part at least, the smallest that can be is just 1/2. So the minimum of this right here, the upper bound, the most this could possibly be, is just going to be when b equals 1/2. And the reason for that, again, is because the nature of this function right here is to approach 1, but just from the top. It's getting smaller and smaller as we go. So because this is bounded, this means that our upper bound for this has to be less than or equal to, on our contour at least, 1 plus if b were just 1/2. So 1 plus e to the minus pi, and then divided by 1 minus e to the minus pi. So this right here is our upper bound of our cotangent. So now let's consider the behavior of our function f. Let's consider the absolute value of f of z right here on our contour. Well, here's the really interesting thing about f. At the start, we said f was going to be a rational function, and specifically one in which the degree of the denominator is at least 2 more than the degree of the numerator. And what this means is that on our contour, quickly redrawing it, on our contour, as these sides of the square just go out to infinity, that means that the absolute value of f right here, it must go to 0, because again, it's a rational function in which the degree of the denominator is 2 more than the numerator. And because of that, just as we take this function and evaluate it at points farther and farther from the origin, the denominator is simply going to grow faster than the numerator. So this right here is actually just going to approach 0. In spite of this, we did still have to prove that this cotangent is bounded, because if the cotangent weren't bounded, this integral is not necessarily 0, but because the cotangent is bounded and this absolute value of f goes to 0, then this whole integral right here is just going to approach 0 as n goes to infinity. So with this result, we can say that this right here is just equal to 0 in the limit, and in doing so we can divide both sides by 2 pi, and solving for what we actually want right here, we see that the sum from k equals negative infinity to infinity of f of k is equal to the negative sum of the residues of g and then at the poles of f. And this right here is what we wanted to prove. So thank you all so much for watching. I had a great deal of fun making this video because it's like proofs and complex analysis. Great things together. And I hope you all enjoyed, and I'll see you in the next one.